Okay, today I'm going to cover structural analysis, sections 6.1, 6.2, and 6.3. So in this chapter, the focus is going to be on trusses, right? And here's some applications for you. So a truss structure like this, which is really just a structure made out of triangular shapes that has long, thin members, okay? Um, so why do we care about it? Of course, we want it to be able to support the weight that it needs to, and we have to design it so that we select the appropriate sizes of the actual members, okay? And how they are connected together too, the connection points. Um, Also, another one is that if you have a given load, how can you design it, all right? How can you design a structure that will support the weight as needed, okay, in the most efficient way possible, okay? Continuing on. So just, trusses, you see them in a lot of different places, bridges, cranes, support structures. Here's another crane. And trusses have a, inherent advantage over just like a standard beam or I-beam. You get strength while reducing the weight, right? So if you have a bridge or you have a structure, of course, how much weight does the structure itself have in addition to the weight that is the load that is trying to hold, right? So if you make it lighter, use less materials, and you also can support essentially more weight with that uh, same structure, since you don't have a weight of the structure or the weight of the structure has been minimized. Okay, so here's an example, a quick example of a simple truss structure and the forces that you'll encounter. Now, what you're going to find is that the truss structures, what they have is they're long, thin members connected together in a certain configuration. And these are pin supports, okay? So they allow rotation, right? Now, one of the things when we start to look at this and think about this is that the forces that are acting on these now, this shows you potentially they have, this is a force acting at this point, another force, another force. So these are forces due to maybe the weight of the roof where it's connected at these points. And these forces here show the reactions at those points. So this would be like in terms of the structure itself, the entire structure, these would be the external forces acting on it, okay? So when we actually go and look, like let's say this force and this force are reactions associated with it. When we actually start to look at and do the analysis, this is the first thing we'll do is the so-called method of joints. And we're going to analyze like a different joint. Like we'll analyze this here. We'll analyze all the different joints. And with the goal of that, what we're trying to do is figure out essentially what's the force acting along this member or this member, right? Individual members. We're trying to figure that out. So we want to make sure that they're strong enough. And they could be, it could be being compressed or it could be under tension, okay? One other thing to note when we're talking about truss structures, at the joints, there's no reactive moment, right? This thing is it's free to rotate. It's doesn't rotate, of course, because it's where it's connected up here and down to here, um, and here potentially, but it's free to rotate. Okay, so there's no reactive moment about any of these points. We only have potentially reactive forces, and the structures that we're going to look at two-dimensional. We might take a look at three-dimensional, but at 2 dimensions, we only have those two reactions, right? The x and the y, potentially, okay? One of the things you'll note over here is the reason there's no reaction in the x direction is because this is a roller support, okay? All right, and we'll see that. If you think about it, it's like, yeah, if it wasn't roller support, this would be one of those redundant systems, right? You wouldn't be able to solve for all the unknowns because of that, all the unknowns because of that. And the last point to make is that for a simple truss like this, you just add like two members in a joint. And for these trusses, the number of members and joints are related by this equation, twice the number of joints minus 3 gives you the number of members. So for example, in this case, right, if you see we have, and either one, right, A, B, C, if you just have A, B, C here, 2 times the number of joints, 1, 2, 3, 6, minus 3 gives you the number of members. If you added D joint here with these 2 members connected to it, what you would find is that now it becomes 1, 2, 3, 4. So there's 8 minus 3, or 5 members. So 1, 2, 3, 4, 5. And there's the 5. Okay. So when we're actually going and designing members or doing the analysis, we're going to think about how the forces are involved, for this type of a structure. Okay. All the loads are applied at the joints. Okay, there's no load being applied like a shear load or shear force being applied like on the side of any of these. Either any of these joints, they're either under tension. I'm sorry, any of these members are either under tension or compression. Okay, any forces would be applied at these points, right? And just real quick, going back to the previous one, you'll notice those are the only forces. They're only acting at the points, at the joints. Okay, going back. Okay. Oh, okay. So they're all joined by smooth pins, right? All right. And this is a good assumption to make in most cases, right? And like I said, their members act as 2 force members, right? So whatever force is acting in this direction at this joint, it's equal and opposite direction acting at this joint. The same thing here. If it's tension, it's like this bar is trying to be pulled apart. If it's compression, it's, trying to be squished together. The bar is trying to be squished together. Okay. Okay. And they just talk about like compressive members typically made thicker to prevent buckling. So there's we have to make sure that, yes, the member can support tension and it can be under compression. So, if it's under tension, of course, then it could be a cable. And if it's under compression, then you might have to do something else to a certain type of member, not a cable, of course. Okay, as before, method of joints. Here's an example. And in this case, you want to solve for the forces in the truss members. Okay. Okay. So same as before, what we're going to do is a kind of an extra step here as we go through. So let's say we're trying to figure out the forces in these members. What's the force in this member? What's the force in this member? And what's the force in this member? We also want to figure out, if they're under tension or under compression. Okay. So we use these equations of equilibrium to solve for any of these unknown forces, right? So here's a free body diagram at joint B, right? So we would make a free body diagram at joint B, potentially at C or A, right? If we get it at B and we solve for this and this tension or compression, the force along this member and the force along this member, then we only need to do one more point to find, the missing one, okay? But here's a free body diagram of B, right? Now, one of the things you're also going to find useful often is to do a free body diagram of this entire structure, okay? And that can help you to find some of the reactions, like to find the reactions at the points, right? So you may find the reactions here, right? Okay, continuing on. Okay, so in general, if the truss support reactions are not given, determine the support reactions. So the first part, like I said, is to go through and do the entire diagram and then look at the external forces acting on it. Okay. So before you actually go in and look at the individual joints, you're going to do the entire structure, right? After that, now from that, what that's going to do is you can use that to solve for the unknowns, like the unknown, either could be unknown forces, depends upon what's given, unknown reactions also. So the external forces acting on this truss structure. Okay. The next thing you do is draw a free body diagram of a joint. All right. So you assume all the unknown forces act on the tension or pulling on the pin. All right. So what we could do is, you can define them, and it's like, what's the direction? Well, you can define them as being tensions. Okay. You might also look at it and determine that they're compression. Okay. But otherwise, you can do this, and this follows the same rules before. It's like if you go through and solve it, and then it turns out that the force is really negative. I mean, your force you solve is negative. Really, it's telling you it's the force in the other direction. Okay, so we need to pay attention to that as we go through. Then you apply the equilibrium equation, summation of the forces in x and summation of the forces in y, both equal to 0, to determine the unknowns. Okay. Oh, and as I said, if it's positive, the tension's correct. Otherwise, it's incorrect. Okay. So if you draw them as tensions, then you could say, well, uh, if the answer is positive, I'm correct. Otherwise, it's going to be in compression. But really, it's a matter of whatever direction you draw it in. If the answer comes out positive, you drew it in the right direction. If not, if it's negative, then it's just in the opposite direction. Okay. So another problem when you go through and actually answer you come up with your answers, you should indicate, like, is this member under compression or is this member under tension? Okay. All right. So you keep repeating it until all the required forces are determined. So until you determine all the unknowns that you need to find. Okay. So often the case when you start to look at a problem, first thing, if there are certain members that are connected with no forces, like there's no reaction and no external force acting at those points, um, and uh, and just looking at it, thinking about it, a couple things is like, if they're non-collinear, means they're not along the same line and there's no external force and there's only two members connected together, that what you're going to find is there's no load on these. And if you think about it and you look at this particular problem, what you recognize here is that, this force is pulling down, but really it's all the y component of this that's under tension that's going to equal that at that point. Okay. This one is, looking at this says, oh yeah, this is zero. There's no, these are zero force members connected to that. So these two are zero force and these two are zero force. This one's a little more obvious, I think, because if you think about it, it's like, yeah, this one has no y component whatsoever, right? This one has no x component whatsoever. So you can, just looking at that one, you can recognize, oh yeah, this cannot be, um, this one has to be, these two have to be zero force members. Okay. So it's one of the things to look at it and recognize what the zero force members are beforehand, because that can simplify things a bit for you. Okay. Yeah, so you could actually show that this is true by doing the equilibrium equations that joints D and A. Okay. And what you would find is essentially nothing's going down. So you remove the zero force members. Now look at the truss. Much easier to analyze this than, at least looking at it, this is an easier analysis than this one. Okay, so the simplification works out really well. Now another case for the zero force members, you'll note here, is that if you have three members together and there's no external force like acting on any of these joints, right? And the third one, so now you have a linear, so there's along a straight line. So this member connects directly in a straight line with this one, with this one. So these are all connected straight in a straight line. What you'll recognize here, it actually should kind of make sense if you think about it. This thing's like on a pin support, and this is on a pin support. This thing could kind of pivot back and forth, right? If you think about it for a minute, what happens is all of the force there's no external forces here. So all of this force is acting straight along this line all the way down. It's collinear. So there's no force acting along from this point to this point, from this point to this point. And like I said, it should make sense to you if you really think about it. It's like, oh yeah, if you're pulling straight on, like if you're pulling a rope and these are two bars that are connected on two pivot points on both sides, you would think, oh, this thing is just going to pivot as needed back and forth, right? So there's no force in these two. Okay, so this is the other case where you can identify zero force members. And as before, now this problem simplifies to this. Okay. So here's an example. We'll start with this. First, check to see if there's any zero force members in this case, right? And what you'll notice here is that looking at this, we've got a line straight across here. These are collinear. AB and BC is collinear. There's no external force acting at B. So B to D is a zero force member here. Okay. So basically, it's just going to simplify to this triangle. All right. So we found one. All right. Analyze pin D, then A. All right. Because in this case, we're looking for force at each member of the truss. All right. Well, this is zero force. That's no problem. And what we recognize then that this one is going to be straight across connected here to here. So really it's just from A to C if you want to think about it that way. Okay, so we have one here, and this long one here. Okay, so we know that. So first analyze D and then A. Well, you could have gone D, C, or one or the other, but D is a good choice to start. You could do A or C. You could actually do A and C. Doesn't matter. You only need to do two of them, though. Okay. Okay. Now, some cases you want to go through and solve for the reactions. In this case, you could do that, and maybe helpful, maybe not. But one of the things you'll recognize here is that when you eliminate this becomes a zero force member. You have two unknowns here. You have your two unknowns here, and then of course, we can come up with two equations: summation of the forces in the x direction, summation of the forces in the y direction, set them equal to 0, and then we could solve for them, right? Then we could solve for the tensions, right? And that's all that's done here. So we have free body diagram to start with. And we have FAD, FCD, right? So then we only have two members here. So we can go ahead and sum those forces. Here's the x direction, so the minus 450, FCD, 45 degrees, cosine, minus FAD, which is also going in the negative x direction, times cosine of 45. That one's equal to 0. So that's my first equation. I have two unknowns. And then summation of the forces in the y directions, minus FCD, sine of 45. Okay, so now we have this one going down and this one going down. We drew them downward, right? So the y component's going down on both of these. So they're both negative. So negative FCD times sine of 45 minus FAD sine of 45 equals 0. Okay, and then you can go and solve for these values. All right. So FCD is under tension, so that was good. We drew it in the right direction, so it's kind of like pulling away from that point. FAD actually turns out, when you solve for this, comes up to be minus 318 pounds. So that one is under compression. Okay. Now what we can do is we're looking for, this member across here, essentially the same. This is just a connection point because it's collinear. So these would be the same. We're going to solve for that. So although the author didn't go and solve for that, you can actually go through and do it. And what you'd recognize is that really this is just connected from here to here. So if you got the x component of this, the x component of A to D, FAD, then what you would find is this is going to be equal to the x component. Okay. All right. Okay, so let's look at another problem. Okay, so first thing is check to see if there's any zero force members. And looking at it and saying, well, are there any zero force members? Well, this one is actually, you'll notice as an external force here, but there's four. There's four connection points here. There's not just three. If you went back and looked at the zero force members, if three members form a joint, that's actually four. Okay. If it was three, then it would be a zero force member. So I'm going back. Okay, real quick. Okay, So the next thing, draw the free body diagrams of D, C, and E. Okay, so if we do D, C, and E, then now we have, each one of these joints is connected to all the members. So that's enough to solve for all the unknowns. Okay, all right. So first thing we'll do is come up with a free body diagram at at, pin D. Okay, and you could have chose a different one if you wanted to, C or C or E if you wanted to, but this one works out pretty well. We have that external force, and what you'll note from this is that there's only two unknowns, right? So because there's only two unknowns, we can use the summation of the forces in the x direction, summation of the forces in the y direction to solve for those. Okay. And just using this 3, 4, 5 triangle, law of similar triangles, we come up with Fx, F of summation of the force in the x direction is just FDE. So the x component of this guy is just going to be equal to this. Okay. So FCD, let's see. Oh, uh, these are reversed. Pause this. I just noticed this is, this should be DE, and this is CD, okay? So this should be DE, FDE, right here. That's what you're solving for. So 600 times 5/3 gives you the 1,000, okay? And then this is FCD, so FCD is 800, okay? All right, so you got two of them. And now FCD, yes, okay. So they drew it, the author drew it correctly here. I'll have to make correction on that in the slides. Okay. So FCD is 800 here, okay? So we know what this one's 800. And now what we're going to do is look at, from this point. And what you notice right here is that these are right along the same line. And this one is only, these two only have an x component. So this FBC is just going to be that, okay? Okay, so the next thing is what we can do is we can solve for FCE. Well, you notice right at this point, the only thing in the x direction is FCE, okay? So FCE equal to, minus 900 equals 0. So just 900 newtons, of course, for FCE. Okay, so now we have 1, 2, 3, and that's the fourth one. Okay, and then the y component, like I said, there's nothing else, right? So it's just going to be the 800. Okay, and having the directions. So the direction of this one means that it's pushing into these points, So this one's under okay, so for the last part here, now we'll look at it at joint E, and then at joint E, what we're going to have is we don't know the tension or compression, we don't know the forces along this member, and we don't know the forces along this member. But what we can do, we can come up with our two equations and two unknowns. We'll have just two unknowns, and here FAE and FBE, and we have the summation of the forces in the x direction equal to 0, and the summation of the forces in the y direction equal to 0. So these two equations are enough for us. Just looking at seeing where they come up with this is that this one's positive because its x component, the way it's drawn, is off to the right. Okay, so this one is positive. And then FBE, this is also positive because its x component is drawn off to the right. This is negative. This x component is negative because this part right here is going off to the left. And this is also negative because it's going in the negative x direction. Okay. Now, the next part is for the y components. FAE is going, that's y components going up. The FBE, the y component's going down, so that's negative. This one's positive. This one is negative. And then the y component of this one, which is also going down, so that's negative. Okay. And the reason in this case we drew, actually you could have drawn this one either way, it doesn't matter, but this one was drawn in this direction because this one was already defined to be under compression, right? We already found that previously. So you take those two equations, you use substitution or something, one variable into another, and you would find out that now you have FAE is 1750 newtons, okay? And it's under compression, right? So that's what the way we had drawn it. And FBE is going to be under tension. And that's the way it was drawn here. So these both signs came out to be positive in this case. So the directions drawn were correct. And that's it.